Can you hear me? Okay. So thanks, and thanks to the organizers for giving me this opportunity to present our work here. So this is joint work with Gustavo Hasso from Bonn. And somehow the goal is to take this class of key representation finite key hereditary algebras. According to Chetnopperman, we understand Japayish, and generalize it, or take some other thing. So what he did is he constructed some examples of detained hereditary algebras. And we want to somehow go the opposite way and remove this this restriction D hereditary. And just construct some of these algebras somehow. That's the goal. Quite modest goal, I wouldn't say, but so now there are no examples somehow, or not many examples, but no for this case. Okay, so the talk is divided in three parts. First, I will tell you something about Nakayama. It's also recorded for most of you. Second part will be higher, and third part will be higher Nakayama. And okay, so notation takes a field. And the algebras are, as usual, associative, unital, finite dimensional, and we consider finite dimensional modules. I think I should say at this point, and we have a duality interchanging left and right modules. Just this from K, blank K. Okay, and so that's the same problem as in Bill's talk. We have to somehow always switch and take this opposite at some point. So for the examples, I'll take rep Q, and this will be contravariant things from Q up. In what case? Maybe. And the examples work a bit better. So that's notation. So let's start with one, recalling what Nakayama algebras are. So in algebra A, it's called the Nakayama algebra. It's called uniserial, so we have this talk by Ed Green about multiserial algebras, so this is some of the AB case of that. If each indecomposable projective and each indecomposable injective has a unique composition series. So these algebras have been studied for quite a long time. And yeah, so let me give you first one explicit example and then some not so explicit examples. So you have equivalent A4, which I start counting from 0 for some reason. So that's Nakayama, but you can also divide out the relation. And then you also have a Nakayama. Okay. and then referred for our tree algebras at several occasions of the conference. So up to stable equivalence. They also. So these turn out in as blocks of group algebras of finite groups. Okay, and there are several known characterizations of this property of the Nakayama algebra. So here I assume K algebraically closed. And the following are equivalent. So first A is Nakayama. Then you cannot ask only the indicomposite projective and indicomposite injective to have a unique composition series, but also all modules have a unique composition series. This is called a serial. And third property is you can completely write down a list of them. So, okay. Not all modules are indecomposable. Okay, if you assume A connected. A is Morita equivalent. The following algebras, so it's either a quotient of a type AN curve, so this would be 0, 1, 2, up to n minus 1. Or a type A n minus 1 tilde quiver, in order to have the same number of vertices. So you have 0, 1, 2, and so on up to n minus 1. And of course by an invisible idea. Okay, so we have that. So you can somehow write down all the algebras you have in some combinatorial way. And the fourth property, you can also describe this in terms of the Austin-Reiten translation. So for each S simple and for each integer j, Lj of S is again simple. Yeah, or 0. Yeah, so all the simple modules somehow lie in a unique tau orbital, let's say. Here. And these algebras are representation finite. And I can write down a list of modules, and to do that I need a definition. So the Cookie series of A is the sequence that underlined, which is equal to L0 up to Ln minus 1, where Li is the length, or you can say equivalently Lerby length of the projective indecomposable Pi, where I somehow assume already that A is given as a quotient of one of these. And giving this combinatorial datum, it's quite easy to write down all the indecomposable modules. Nakayama algebras. Are representation finite. And the indicomposable can be indexed in a certain way. So we have integers. Oh, okay. I should say that from now on I concentrate on the type A case. The type A tilde case is very similar, but needs some more setup. So just talk about type A. By tuples mu2, mu1, where 0 is smaller equal mu2 is smaller equal than mu1 smaller equal than n minus 1. So this would be representations of the AN quiver. Of course, always linearly oriented, as you can see in the theorem. But then you divide it by relation, so you forget some of the modules over that. So what are the modules you forget? So whenever there exists a j such that Lj minus 1 is bigger or equal than Lj, then you forget all the modules where mu2 is smaller or equal than j minus Lj, and mu1 is bigger or equal than j. So these are certain hyperplanes if you want. So if we are in this example, and here of course L is the Kubic series. So in the example, you would have the Gaussian right quiver of type A4. Just with a strange index instead maybe. And then what you do, so the Kubic series is 1, 2, 2, 3 with my convention that representation of Q are contravariant functors. Then you see there's only one place where L1 is bigger or equal than L2. And what you get here is that you have to forget all these two indicomposable modules. And then this is your module. So you can also describe somehow the errors if you want. So this is somehow a restricted root system of type A2. So the arrows give you somehow the irreducible morphisms here. So this may be alpha 1, alpha 2, and the tau translates given by some alpha 0. So somehow combinatorially describe the whole module category. Okay, so that's the first paragraph in Nakayama algebras. We come to the second paragraph in this somehow in AR theory, or also called cluster tilting theory. And for that, let me recall this theorem. Ausmann was also mentioned in Crowley-Lewis lecture. So if you have representation finite algebra, lambda, you can, so it has a finite number of indecomposable modules, so you can sum them all up. So this comes with a module M, which is the sum of all the indecomposables. You take the endomorphism ring for that. That's it. Depends on your convention. dimension of left to right modules. Okay, and what you will get here is algebras gamma with a global dimension of gamma is smaller equivalent to a dominant dimension. Gamma is greater equivalent to. So dominant dimension, let me recall that. Supremum of all numbers S such that there exists an exact sequence 0 to gamma to I1 to IS and the IJ of it. So you can embed your algebra in a projective injective module and the process is G again. Okay. And this remarkable theorem has been generalized. By Nakayama. But let me do some definitions before I can say this. So we need the definition of the cluster tilting subcategory that we saw already several times. Let me recall it. So module M in mod lambda is called D cluster tilting. If all direct sums of M are equal to N such that they vanish and for all I between 1 and D minus 1. And it's also equal to the same thing, but with the modulus here. So we saw this definition for D equals 2 in the Amio's lecture series, for example, last week. You were there. And there she didn't need the second assumption because the heading was too kind of a young. In general, you need this. Okay, and then we call it algebra weakly D-representative finite. If there exists such a cluster tilting module. Okay. And then Yama's generalization of this theorem says that the weakly D-representation finite algebras are in one-to-one correspondence. This is one-to-one. With the algebras with global dimensions smaller equal than D plus 1 and dominant dimension greater equal than D plus 1. Yeah, what you do is if you have some of the same construction, if you have an algebra lambda with a cluster tilting module M, what you do is you take the endomorphism ring. And in both cases, the reverse thing is given by the algebra gamma to the endomorphism ring of the direct sum of all projective injectors. So some remarks, what is similar, what is different. Sorry? The module M here is the cluster tilting module. You have gamma, and you send it to the anamorphism ring of the direct sum of all the projective injective gamma modules. Yes. This is representation 5. This is. What's the module for that? Yes. Yes. This is a cluster tilting module regardless. Yeah.
Module is on from that module into it.
Yeah. So on from gamma.
Other way around. Direct sum of Q's to gamma.
Thank you. Okay, so I want to just tell some remarks. So if D is equal to 1, then, okay, the notions coincide. So there exists one CTM, if and only if there exists a module M such that at M is equal to 1 lambda. Right, why is that? Because this condition here is empty if D equals 1. By convention, this condition is empty, and then at M is equal to the module category of lambda. Okay, so weakly one representation finite is the same as representation. So awesomeness work is generalized here. And the second thing, so we can see already from here that it does not necessarily exist, such a cluster tilting module. Also in the highest setting that's true. So even if the CTM exists, it is in general not unique. Okay. Right, so easy examples, for example, projective algebra, type A, 3, so it has several cluster tilting. Okay. So there's a third thing, so this D representation finite D hereditary algebra. So a weakly D representation finite algebra is D hereditary. If the global dimension lambda is smaller. Okay, in this case, Yama proved that in this case it is unique. So D hereditary implies that this M is unique, and you can write it down. It's just shifts of the injectives where tau D is not the Austen-Reiten translation, but what's called the higher Austen-Reiten translation. So it's tau composed of all. Sorry? So so this is what I would call D-representation finite, D-hereditary. I will not call it D-representation finite because I think, so it's somehow, agreed that this should be the analog of a representation finite hereditary algebra, so we call it D-representation finite, D-hereditary. But this condition somehow is too strong. So we want algebras of higher global dimension that behave similarly with respect to representation theory. Somehow. They behave like modular categories, but somehow from a higher perspective. In a higher case. So for the next term, there's no agreed terminology. So we call it in our paper DZ representation finite algebras. So it's 4 in algebra. It's called DZ representation finite. And it was introduced before in a paper by Yama and Kaso under the name homological, the cluster tilting subcategory. So if you have your cluster tilting module, and since M is an odd M, of course the xi between M and M vanishes for between 1 and d minus 1. Right? And then they might exist some for D if it's somehow interesting. But for D plus 1, it's not clear whether there exists some or not. So one could somehow ask that this is 0, then I is in D times M. It's not 0. So the only homology is some multiples of D. It might seem strange, but we've shown that this is equivalent to the following. So 4 is equivalent to other facts. So first we could ask that omega d of m is again in at m. We could ask the dual property that omega to the minus d of m is at m, and then write this down. And you can also ask that in certain existence result of long exact sequences. So for each x in at m, and for each sequence 0 to L to M1 and D to N to 0, so with D plus 2 terms, there exists an exact sequence zero to Hom XL to Hom X1 and so on to Hom Xn, and it continues with X1 XD XL XD XM1, and so on. Right. And then you go to X2D. You can imagine how it's going to be. X2D. And so on. So if you want to do homological algebra, you might want long exact sequences in homology, and somehow this is the condition that guarantees that, plus the dual. So more precisely, the goal that I stated in the beginning was to find nice examples of DZ representation finite algebras. And why might we want to do that? So the goal is still to develop some nice theory of goals. Of cluster tilting categories. Yeah? D cluster tilting. And in order to develop a nice theory, it's better that we have some examples for this theory. So, first of all, somehow to justify why we are interested in that. But also, if we have some conjecture or guesses what might be true in this setting of D cluster tilting theory, then we have to test them somewhere, right? So yeah, that's why we ask for some examples. So the theory, I mentioned only a few words. So Geiskeller and Oppermann have this theory of D plus 2 angulated categories that fits into the setup. There's the work of Crasso about D abelian and D exact categories. So there's some sort of theory. Which would need examples, and there are also some examples, mostly in the D representation 5D hereditary setting. So there are examples which are analog somehow to one case, and there are also some algebras which don't have a one analog that still exist. So come closer to Nakayama algebras. I mention one class of examples that can be constructed. It's constructed by Yama in one of his first papers on the theory. So if you have some positive integers, d and n, then you can define inductively some algebras. As follows. So we start from the hereditary Nakayama algebra, so that's A again. And then this is represented finite, so it has a cluster tilting subcategory, one cluster tilting subcategory, namely all of direct sum of all of its modules. So we can take its Ausländer algebra. In general, we can take somehow this Ausländer algebra, or this D Ausländer algebra if you want, of the step before. So now for this makes sense, somehow I didn't specify modules, so it better be a unique one. So the theorem is that this is D representation finite, D hereditary. Okay, so in each step you can take the Ausländer algebra without ambiguity. Yeah, just the unique cluster tilting module, take its endomorphism ring, and then you have the next one. and you can classify the indecomposables in this cluster tilting module are indexed as follows. You just take an n-restricted root system of type D. D plus 1 up to 1, where 0 is smaller equivalent to D plus 1, smaller U1 is smaller equivalent to minus 1. So let me give you an example. This is now the same example as before. So B equals 2, and then A4. So this is A4, 2. Okay. Take some time. And the errors are again somehow adding a particular one in a particular component. So it looks like that. Okay, maybe you want the relations. So the relations are always when you have such a thing, then there will be a commutativity. So also if you change it, and if you have such a thing, and this thing doesn't exist somehow, then this would be zero relation. So for example, you would have a zero relation here, zero relation here, commutativity here, commutativity here. And these algebras have been nicely described in work by Oppermann and Thomas. So they have many results about the properties of these cluster tilting modules, OMs, X1s, and so on. And our description somehow is just a shift of their notation. There. And now we want to come to our third part and describe higher Nakayama algebras. So remember, in type A, these Nakayama algebras were just quotients of this AN quiver by admissible ideals. So the question is, what is the correct analog of the admissible ideal of this setting? And it turns out, in this case, at least, it's an idempotent quotient. So the key lemma that we use is the following. If you have an algebra and M a D cluster tilting module and E an idempotent. Satisfying two properties. So first of all, we want that A module of the idempotent as an A module and its dual are really inside the additive closure of M, the direct summons of M. And second of all, so this is somehow the weaker condition you might have many occasions, but the second one, I think the examples we have are the only ones that we know. If you take an indecomposable module which is not annihilated by E, then it should be projective injective. So corresponding to it would belong to art E intersect with art A. So these are the two conditions. And as I said, the first one we know many examples or some examples of, but the second one we only know this one example. So choose an additive generator of M at M intersected with the module category of A mod E. So suppose at N is at M intersected with the module category of A mod E. Then N is a class D cluster tilting module in mod A mod E. And the proof is not so difficult. Just somehow some homological algebra. The assumptions are quite strong. So if you know that something has vanishing X with everything that's not annihilated by E, you automatically know that it has vanishing X with the rest. But it's somehow the second condition. And the first condition you somehow need in order to have the projectives and the injectives. First define the object in the main theorem, and then say the main theorem. So, the higher Nakayama algebra as a set type A is defined as the quotient of A and D by the idempotent ideal corresponding so the vertices of this path algebraic relations are indexed, as we saw in the theorem, by mu d up to mu1, right? And here we ask precisely what we had in this definition, in the description of the indecomposable modules for the Nakayama algebra. So there exists a J set that Lj minus 1 is greater or equal than Lj. Mu d smaller or equal than J minus Lj. And mu1 is greater than. Okay. And then the theorem is, these are examples. So if we call that algebra A L subscript D, then A L subscript D dz representation finite. Yeah, its indecomposables are indexed let me just say similarly. So you just take here mu d plus 1 and then have here mu d plus 1 as well.
Question, what are the LJs?
Sorry?
What are the L sub Js?
So L is a Kupic series of the classical Nakayama algebra. So you can describe them combinatorially as well. So just take some that corresponds to it. Yeah. And this is LJs are then the components of this. Okay? And in some sense they behave like Nakayama algebra. So for all simples in Rm, you have that tau d of s, tau d to j becomes s, is simple, of course, or 0 for all j. So how do we use the key lemma to construct these algebras, and what are they in the example? So let's take the same example that we had before. So n is equal to 4, and the Kupic series is equal to 1, 2, 2, 3. So which idempotent quotient do we have to take? This is not the idempotent quotient. Anymore. Sorry. So what would be A L2? This should be this algebra modulo these two idempotents. So now you factor out these two idempotents. So these become zero relations. And of course you have the other mesh relations. And the theorem says this algebra has a cluster tilting object, and the indecomposables are precisely given by, you brought out some of the same thing. So you move this whole strip plus this strip. So there are several projective injective which have 0,2 or 0,3 as a composition factor. So these are the ones that contain 0,2 as a composition factor, and these are the ones that contain 0,3 as a composition factor. Okay. And then the subcategory you get by removing these somehow is the module, is the cluster tilting module. Okay. So yeah, this is somehow the M L2 cluster tilting module that comes to that. Yeah.
Speaking about these algebras as if they had a unique cluster tilting module.
No, they have not in general. Okay. So these are representation finite with this particular choice of the cluster tilting module. Yes. Okay. So let me just say in words. For the type A tilde case, we use a theorem by Dapo and Iyama, which is similar to Riedmann's construction of representation finite self-injective algebras. So you take an infinite type A quiver, type A situations where here and fold it somehow around. And And yeah, so in this way we construct these examples. Thank you.
Are there any questions?
So for the type A tilde, you have another version of
In general, not, as not all type A tilde Nakayama algebras are. You will get self-injective algebras, yes. Some of these self-injective. And then, of course, they are periodic by your theorem. And so one of our next projects is somehow to describe which period they have.
Are these higher Auslander algebras of smaller higher Nakayama algebras, or?
No, they're not.
Yeah.
No. Yeah. So it's a strange thing that you have. So in order to get the algebra, you have to take the quotient by these idempotents, and in order to get the plus tilting module, you have to take the submodule somehow, or the sub category that is supported on the other vertices.
Following on from Eric's question a little bit, the statement in your theorem about the simples, does that hold only for the plus tilting module you induce down or forward?
I think it only holds for this, at least there I'm sure. It's a bit strange because plus tilting modules in general do not need to contain any simples. So somehow in this thing up, yeah, then it holds. Okay. Yeah, so it's a bit also strange, and it's not clear whether you can characterize these algebras by these properties. I don't think that's true.
Is there someone categorical characterization, modulation characterization, higher Nakayama?
We don't know any. We try to find something like this, right? That there are always some sort of. So the main problem is that we can't define what a composition series is.
Yeah.
Because we don't have x1. We only have xd. And yeah, so there's no composition series. And also this fails by these somehow, what I said. There are plus tilting subcategories without any simples, and you probably wouldn't consider them as Nakayama algebras somehow, or module categories of Nakayama algebras. So don't expect such a theorem, but I hope there is such a characteristic.
Any other class of this research
So Gustavo constructed before the ones somehow with radical square 0. So you have, if you mod out everything that is above, so and you have somehow radical square everywhere. So this was known before, but this is some of the first example I know of. Yes.